Hello guys and welcome back. I believe that last time we've worked on mapping our kernel space. So today I want to focus on passing the memory map into our bootloader or boot info struct so we can pass it along to our kernel. So I guess let's get straight to it. Right, so let's start by removing that autofix since we are going to start using it. And let me just go ahead and remind myself of the struct of this mmap or boot info struct. So at the end here, we've put this single item array, which we call mmap. And this is where our mmap entries will be put. Right. So I guess we could go all the way down here. And the first thing I want to create is const and call it mmap entries. And this obviously would be a mini item a mini item slice of boot info mmap entry, and of course this will get boot info.mmap. The pointer to that would be cast to that mini item pointer. We would also like to have a variable so that we can track which memory map we are writing to. So mmap index, I'll call it, and this would be a U64. Sorry, not 0. Yeah, so that's pretty much it. So let's get started on this. The first thing I want to do here is we know that our boot info struct has a maximum length of one single page. So we need to check if we are crossing the page while writing our memory map descriptors, because it can happen if we have a memory map that's too fragmented. So let's do a check for that. So if boot info.size, we have a size on that, is larger than constant's arc-page size, minus the size of what we are trying to write, which is size of boot info mmap entry. So mmap entry should be 128, 64 and 64, so 128. So if that is true, we would like to, first of all, return a bootloader error, which would be something like memory map too big, something like that, and then probably just log an error, which would say something like memory map is too big. Yeah, something like that. I can live with that. Right, so now that we have this out of the way, what we need to do is, so here we get our descriptor. Here we do print some info about our descriptor. We'll get rid of that in a bit, but for now let's leave it in. And what we would like to do is, well, just write our memory map entry. So let's create a const mmap entry, which would be a pointer to mmap entries at index mmap index. Right. And we are going to write to this entry. So we have size and pointer, And we also need to encode the type into the pointer. Yeah, so what I'm going to do probably is, can we go there? And I'm going to do something like this. I'm just going to use the type system a bit. So create. So this create function will take a pointer, which is a U64, a size, which also would be U64, and a type, which would be, well, let's create a type enum then. And this would return a map entry. Right. So this would just return something like this. And I guess I'm going to need to create our const pointer with type is this should be U64, but this would be pointer plus so int from enum type. There we go. Right, so let's create that enum. So const type is enum, and we know that this enum here would need to fit into 3 bits for the simple reason that the pointer is page aligned, and page alignment means that the address is a multiple of 0x1000 hex. So that means that the lower 3 bits are zeros, and that's what we are using to encode our types. So to get the types, I guess I'm gonna go ahead and do bootinfo.c or .h. There we go. And I guess I'm just gonna copy those over. So used, not user, used, free ACPI, reclaimable boot info. Right, so here we have 8 of those, and starting from 0, so we go from 0 to 7, and basically those are all the values that we can encode into 3 bits. If we add any other value, we'll need another bit to encode it. So yeah, we'll need to fit our classes into these. Right, so this is our pointer with our type. So here we can do pointer is pointer with type, and size is obviously just size. There we go. There we go. So what is the problem with this? All right, a map is written this way. Right, so let's also create a few other functions. So get pointer, which would take self a map, entry, and return a U64. And this would just do, so let's get const type mask, and this would be 0xFFF, lower few bits. Let's just set this to U64. Let's get the pointer mask, which would be, well, just the inverse of the type mask, and then let's return self pointer and it with the pointer mask. There we go. That should be fine. We could do pub function get size. This is pretty trivial. Entry returns a U64, and this guy here just returns self.size. All good there. Right, and here go pub function get type. So self mmap entry again, U64, and this guy here would just I guess I'll just get this from there, and we could do return self.pointer ended with type mask. And of course, this here would just need to be type. Oops. And this here would need to become. So what's it called? Enum from int. Yep, from int. There we go. So let's format those, and we should be good to go, I think. Right. So here, what I'll do is I'll just deref that entry, and I'll create a new one in its stead. So boot info mmap entry dot create. So the pointer is descriptor dot physical start. The size would be descriptor dot number of pages multiplied by constants arc page size, and our type would be entry type. So we need to compute that entry type somehow. So let's do const entry type is, let's switch. So this logic here will need to become complex, I think. But for now, let's just do the simple thing. So let's switch on descriptor dot type, and we'll see where we. So basically, the general case, we want this to be boot info mmap entry. Actually, hold on, let me do it this way. So this would be boot info mmap entry type, right? And this here would be used. So in the general case, actually, let me just write this, because this is Zig, not Rust. So here we need to actually switch on the types. So let me just go ahead and take a look at what we have there. So these are the types that we have. And I think that these ones would be free after our bootloader finishes running. With this one also, conventional memory, this should be free. The ones marked ACPI should be marked ACPI. And I guess all the other ones would be marked as used. Right, so let's just copy these over. Let's put them there, and let's just join all of them. Right, and let's just do this would become this overall. Cool. And this would be free, I think. And to that, we're gonna add conventional memory, and that should be it. Right. I guess we're gonna need to do this. Okay, so I guess that's for that. Let me just bring up that again. These two here will become ACPI. Yeah, so let's do this and let's do that. So this would become ACPI. And that should be pretty much it. So when I was talking about this becoming more complex, I meant that for our purposes, we also needed to mark the reclaimable regions that we might want to use or not. We wanted to mark the boot info as boot info, the frame buffer, the kernel, and the paging. And to do these, we will actually need to compare to see that our address or the address of our of the pages pointed to or described by our descriptor would fall within the range of where we've allocated our things. So the kernel, for example, or the frame buffer. So that would need to be done separately. So let me just do a to-do here. I'll get back to this afterwards. Mark kernel fb env boot info with the appropriate type. Right, so for now, let's just use the actual type that the descriptor has given us. And this looks like it's doing the trick. Now, the problem we have, so I guess we could do mmap index plus equals 1. So let's just increment that. Or actually, we could put that into here. No, I have my doubts about that, so let's keep it here for now. Now, the only problem that we have is that, well, actually not a problem, but we might have memory maps that have different types here, but we would map onto the same type. So we'd have a boot services data region that's right next to or contiguous to a conventional memory region, but we'd mark both as free. And we'd get two separate fragments on our memory map, which we don't really like to have. We would like to have a memory map that's as consolidated as possible. So to go around that, I think what we need to do is remember the last mmap index that we've worked on, which would probably be mmap index -1, unless we get quite a few that are contiguous in a block. So let's just create a variable for that. This would be an optional U64 that starts as null. Yes, that looks like a good thing to do. So here, if we actually have a last mmap index, let's capture that as last index. So what are we going to do here? If our so what are the conditions under which we merge the current one to the last one? We want to have, first of all, the same type. So mmap entry dot get type would need to be the same as I guess here we need last const last mmap entry, which would be a pointer to mmap entries of last index. So if that is last mmap entry dot get type, and we would like to have mmap entry dot get pointer. So we want to get the end of the entry. Actually, get pointer, get size. Let me add something else here. Let me do get end. I'm not sure if we're gonna use this a lot, but let's for now just create it. This would also return a U64, and this would just do a bit of math. This would do return self dot get pointer plus self dot get size. Yeah. So and I guess I'll use that here. So get and. So if the end of one entry is equal to, or rather the, hold on. So the start of the current entry would need to be the same as the end of the last one. Yep, that's right. So get end of the last one. So if this is true, then we will need to get last map entry, get its size, and extend that size by the size of our current map entry. Right. And we also need to get our mmap entry, and we just set its pointer to 0. I'll just work on the field directly here. And this one dot size is 0. Cool. Right, so once we do this, I think we just want to hit this with a continue statement just to ensure that we short circuit the loop here. So if this is not the case, and we need to actually create a new entry, we would like to just set the last mmap index as the mmap index, the current one. Right. And here I think I'm going to pretty much do the same. So this else block here would just be for this. This is basically what would be executed on the very first loop, or the second one, because we have no last mmap index. I actually want to add a few log entries here just to know what's going on. So let's do that. So log debug, and here I want to do extending last mmap entry contiguous. And what should I do? I guess I should print the mmap entry itself. Mmap entry. Yeah, that looks pretty good. And let me just do this. If we don't go there, we go here. Otherwise, we go here. So here we want to not extending, to add this information, not extending last, or rather, let's do creating a new mmap entry. And here we do not contiguous to the last one. And here, creating a new mmap entry, and I'll do no last. Yeah, or rather, let's do first iteration. There we go. Right. And so here we get our mmap index incremented, and we go again. Cool. That looks pretty good, I think. Right. So I guess let's go back to our main. There we go. And let's see where we get our memory map. That should be about here. And if we probably just go ahead and do const mmaps or mmap entries, and this would be a main item pointer to boot info mmap entry. And to this, we are going to add, or rather, we are going to create this from bootinfo.mmap. Right, and here we are going to, actually, let me do something. Let me just catch the error here because I'm interested in what error we got. And this would just be E. And let's do stdlog debug boot info, or rather mmap, and actually let's do something like this, and let me just go ahead and do 4 mmap entries. Let's just get the first 5 items from that to mmap, or let's call it entry. And let's print something for that. So log debug. And I guess I can just do something like this. And entry, and then something like this. Right, so this would be I, and this would be entry. And obviously here I need to do something like this, and add an I there. There we go. So problem solved. Right, so that's in case we get an error. And what I'd like to do also is pretty much the exact same thing if we don't get an error, just so that we know what's going on. Actually, let me just do all of these as error, just so that we know to differentiate between the two. Right, so let's build this and see what we get. Oh, right, so few errors. No error named memory map too big. That's actually right. So let's fix that. So memory map too big. All right. Type is not pub, and yeah, all right. That's it's fairly easy to fix. So we just need to go over here, mark this as pub. All these functions are marked pub, so that's all right. Too few arguments to format. Too few arguments. Okay, well, can't you give me a bit more context? Where did we do something like that? I guess it's in here somewhere. Too few arguments. Yeah, I'm not seeing it. Right, okay, I see it, I actually see it. So this one needs to be that. All right. Okay, well, it actually builds, which is always a bit surprising. Let me just do something here. Let me just go ahead and remove this, and let's see what we get. Okay. Okay. So let's see here. Got memory map. Memory map is too big. Okay. mmap has pointer 1, size, whatever. Okay. Okay, so let me actually go ahead and preprint those things. So start is 0x hex, the address, and size is 0x and also hex the size, and type would be, well, just whatever the type is. So this would be get pointer. This would be entry.get size, and this would be entry.get type. Right, let's try this again. Okay, probably I'll probably want to. I will probably want to go over to memory map. No, not memory map. To actually to main, and go all the way down, and probably just comment out this here. Yeah, just to make this process a bit faster. Right, okay, so now we have this a bit more readable. So we know that our first entry here type is boot services code, which we would consider free. It goes from 0 to and has size of 1 page, so 1000 hex. And then the next one is conventional memory, goes from 1 page to well, it has a size of 9F pages. So we also consider that as free, and we should then collapse these two into one single free block. So that starts from 0 and has a size of whatever that is. I guess there's 1 page missing there. There is 1 page missing there because this is 1 page and this is 9F pages. Yeah. I don't know if this is the actual size, or I guess this is the end. And if it's the end, then we are good to go because we go from start to end. Yeah, that looks okay, I think. If it's the end, it looks okay. Then we have another block of memory which starts at so 10,000 hex and ends at 8,000 hex, which we do have, and we have it marked as free because it's conventional memory. But then we have these things here. And we only have, so this one here has 0, so we know that this one here is not something that we've written to. Huh. Very weird. Okay, so let me do something. Okay. Right, so let me do something a bit different here. So I'll this page we've allocated here, we don't know if it's zero initialized or not. So just to make sure that we have a zero initialized page, I'm going to use the mem helper. Allocate pages, pages, and I'll ask just for one. And obviously this one here can fail, so let's catch whatever error there is and probably just yank that, put that there. Yeah, let's change that. Say could not allocate a page for boot info struct. There you go. And let's remove those. Cool. So now that we have our boot info page, we might want to basically pointer cast it in place to boot info. Right. So now we don't really need any of these anymore. Now we are pretty sure that our boot info page is zero initialized. Actually, this one here can become const since we're not touching that in any way. Right, I'll also do something here. I'll go to mmap and I'll do something like this boot info dot mmap entry, and I'll create a pointer which will be 0x and a size of, let's say 1, 2, 3, 4, 5. That looks okay. There we go. And this is just to mark where the memory map starts. And what I'll do next is right before I write the memory map to boot info, so right before I call this, I am going to log debug and just dump the memory map entry, or rather the boot info page, so boot info page, and I'll dump as hex, I guess, the few first bytes of that. So boot info page, and let's dump about 200 bytes from that. And of course, here we are in main. So stdlog is what we want to use. Right, so now that we have that going, we are going to go to get memory map. And I want to actually track the size of our boot info struct. So log.debug boot info.size is equal to just as a an int, and I'll put here boot info.size. There we go. Just to track how the size grows. And actually, I'm just noticing something here. We've never actually increased the size. So we do have a bug in our code where the size doesn't increase with every entry we create. But we still get memory map is too big. Yeah, that's a bit worrying. Okay, let's fix that first. So size is plus equal size of, I guess it's, yeah, so it's boot info.mmap entry. And I think this one here is fine. We don't need to increase the size there. Maybe we do. Maybe we do. Maybe we want to do that. So let's just put it here and see where we get. So the only case where we don't increase the size is this one here, since we've written to the last entry that we've written to, and the continue will short circuit this so that we don't increase the size. Right, okay, fine. Let's build this again and see where we go from there. Okay. Right, so this script size, okay, so that's fine. So we have a size of 96, which is the size of just the boot info without any memory map entries. Then we find our first entry here. We bump the size by 48. That looks pretty good. Then, no, actually not 48, by 16. By 16, yeah, we have 16 bytes in our map entry struct. So that's 16 bytes. And then we have this second entry here, but this one is contiguous. But why does the size go to 0? Actually, okay, hold on. So we are dumping the boot info page before we write the memory map. Hold on, what are we expecting first of all? Let's make sure to know what we're expecting. So we expect our 4 magic bytes first, then the size, the loader type, and all of these should be filled by now, since we've already filled the frame buffer. So the only thing that we need, that we won't have, is the memory map by the time we print the page. Except that here at the very top, I don't see the magic bytes. Actually, I see them over here. Okay. Our pointer is there. Our dummy pointer that we've created for the mmap in main. So which one was it? So this one here, AB, 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 is what we see over here. And, oops, and the size, the 1, 2, 3, 4, 5 size is this, I think. But the order of the fields is not respected. Okay, well, that's if that points to something, it points to the fact that this structure that we have here is not packed as it should be. So I think I will be obliged to do something like this equals packed struct, and let's go over there, do something like that. Yeah, I think I'm gonna be obliged to do something like this. And actually, let me just bring everything into this one here. And we are actually going to need to make some changes. So let me just go ahead and look for bootinfo. Well, actually, as text, let's grab for bootinfo.zig. And all of these would need to get this added to them. Boot info. And this one here also need to get the boot info. Okay, so let's build. We probably will have a few errors. Boot info is not marked as public. That's actually fine. Boot info.zig. We should go up there. Hit that with the public. All right. So packed structs cannot contain fields of type arrays of U8. Okay, so we cannot have arrays in packed structs. Okay, well that's actually pretty fine. we could replace the array with let's see here. We could replace that by a U32. And here we just need to compute, actually, we don't need to compute anything. We just need to copy these bytes here. There we go. And just bring them over there. And we just need to do something like this. There we go. And this here would just need to disappear. I guess that fixes it. We also have this here. 3 times 8 is 24. So 8 times 31 is 248. That needs to become a U248. And 24 times 8 is 192. So that needs to become a 192 or a U192. So this one here, though, would be, I guess, just an mmap entry for now. And let's let's rebuild this and see. Backstruct's going to contain fields of type optional U64. Okay. Type has no guaranteed in-memory representation. Fine. So I guess all our optionals would need to become just regular ints. So this one would be that, and I guess all of them would need to be enum from int, int, not env. Okay, so this one would need to become a 0. This needs to become a 0. So it does this one, and so does this one. Okay. Let's see here. Backstructs cannot contain fields of whatever. Right. I guess we could mark this as backed. And we should not have any problem, since the backend would guarantee the memory layout. Yeah, okay, that worked. So expected type thingy in main 38. So main 38. Yep, okay, that's actually pretty fine. No, actually, let me just remove this and remove that. Okay. Expected optional found U64 in main 104. 104. Right. Oops. And this one here too. And this one here too. Right. Expected type thingy found other thingy. Okay, so main 115. Okay, so here we do need to pointer cast. Oops, cast that. Yep. And now in mmap we need to do the same. So 49. So add pointer cast, and we need just that there. Oh right, we are getting closer to something. Okay, so at least it builds. Let's see what we get now. All right, so we don't have any problem anymore. We don't get the error. Let's see here. We go through quite a few mmap entries, and so not contiguous. So we create a few of them, and then here we have contiguous. So the size stays the same since we are basically writing to the same entry. Right, so all of these would have the same size. And here we'd have a new one. Yeah, that looks pretty good, I think. And let's actually take a look at what our boot info page looks like. So here we have our magic bytes followed by the size. So 60 is 96, I think. 96, yep. Yeah, so that looks pretty good. So here we have our dummy pointer, and that looks pretty good. So I'm just going to need to go ahead and change the printing for the non-error case. So let me just grab these and put them there. And let's do about 20 entries, just so that we are sure that we are not doing something weird. Okay, well, that's it's building. It's something. Okay, so we have about 15 entries that are filled. The other ones are just zeroed out, so they are not written to. That looks pretty good. Let's check on how much memory we are mapping actually. So here we have a first free page, then we have a second free page. I'm looking for what's the largest free area that we have. And I think it's this one here, 61B3 and 30. So 0x61 B3 and 3 zeros. And that's about 100 megs of RAM. Okay, so let's check how much RAM we have. So Shift Q to go here, and well, it doesn't show here, but it should show over here. We do have 128 megs of RAM on this virtual machine. So let's do something actually. Let's go ahead and add some more RAM. So -M, and let's say we want 1 gig of RAM. Let's do 2 gigs of RAM. And let's see if we are going to map all 2 gigs. So no errors, and we still have our mappings. And here, I think this one here is the largest free area we have. And if we check, so 7E, 7E, 1B3, and 3 zeros. That should be, yep, 2 gigs. 2 gigs. And if we Control Q here, we have 2 gigs of RAM. So I think we are looking pretty good. So we are pretty much done with what we wanted to do today. The only thing that remains is doing this, so marking the regions of interest that we've allocated with the appropriate types. As I said at the start, we could actually add logic to this code here to check that we are within bounds and do the mapping that way. But it would be a bit wasteful as I thought about it, I found out that it could be a bit wasteful because we could have pages that are part of a larger block, but that are also part of our frame buffer mapping, for instance. And we would need to either have complex logic to fragment that block into smaller blocks, as what we did in the BIOS side, where we've written a fully fledged memory allocator. Or we could go, the easy way, where we mark the whole block as frame buffer, but that would waste quite a bit of memory, I think. So it's not really ideal. So as I was doing this, I actually thought about a new way that I want to try to make this work. In the UEFI spec, the memory types that are put here, as we can see here, the memory type enum is actually not bounded. So this underscore here in Zig means that we can actually add entries to this memory type. This max memory type here is the limit. So these are the memory types that are used in the spec that the UEFI services know about. But we could actually specify our own types. So I want to use this as a way to distinguish which blocks are our regions of interest. So I'll mull over that for a bit. Well, that's pretty much it for today. If at any point you've liked this video, subscribe, like, and comment. In the next one, we are going to try to clearly identify our regions of interest in our boot info memory map. Hope I see you there. Fucking out.